Welcome, everyone. This is a class tonight, so I'm going to call you my class. We had read for us just now Romans chapter 1, verses 18 through 20. That's the theme passage for this series. I start with that when I'm doing this series in a church building. Most of the folks who would be here in this setting would be folks who believe the Bible is the Word of God, as do I. But if I were doing this lecture in a science lecture hall, I would not make any reference to the Bible whatsoever. I hope that doesn't offend anyone. The reason I won't is because of Romans 1. Verse 20 says, "Since the creation of the world, His, that is God's, invisible attributes are clearly seen, being understood by the things that are made, even His eternal power and Godhead, so that they are without excuse." What the Bible teaches, ladies and gentlemen, is that the natural world has sufficient testimony to convince people that there is a God. That's what Romans 1:20 says. So the Bible itself says one can conclude there is a God by examining the things that are made. Therefore, you don't have to have this book to become convinced there's a God. And when I'm speaking to folks who don't even believe God exists, it is of very little use to quote from the book we call the Bible, because they don't even believe God exists. So the place to begin is the evidence of the natural world, it seems to me. Thank you for being here tonight. I have quoted to you from Romans chapter 1 to show you the biblical basis for what we're going to do tonight, tomorrow night, and Wednesday night. It has been a passion of my life to study the natural world. I'm a firm believer in the wonders that can be produced through science. Science is critically important to human beings. Man, as made in the image of God, has been able to understand the natural world because of our capacities given to us by God. But science does not begin with a revelation from a book. It begins with the evidence of the natural world, and from that it draws conclusions. So, again, I say, don't get offended if I turn now from this book to God's other book, the book of the natural world. The title of this series is Origins. Is it reasonable to believe in God in this scientific age? That's a good question. And I can tell you that many, many people, particularly in colleges in our country and around the world, would say the answer to that question is no, it is not reasonable anymore to believe in God. So I start by quoting to you from a book called The Blind Watchmaker by Richard Dawkins, the same man who wrote the book The God Delusion, who takes the position that not only is religion and belief in God foolishness, but it is dangerous, and there should be no patience with anyone who believes in God. His answer to this question is absolutely not. In this age of science, the watchmaker of my title is borrowed from a famous treatise of the 18th century theologian William Paley. His Natural Theology, or Evidences of the Existence and Attributes of the Deity Collected from the Appearances of Nature, published in 1802, is the best-known exposition of argument from design, always the most influential of the arguments for the existence of a God. tonight, tomorrow night, and Wednesday night, I'm going to be making the argument from design. That's what this is. Dawkins says Paley did a pretty good job of that in 1802. Kids in college and high school, if you were in a college in those days in England, you would take William Paley's Natural Theology. That was required. It is a book I greatly admire, says Dawkins, for in his own time its author succeeded in doing what I am struggling to do now. He had a point to make. He passionately believed in it, and he spared no effort to ram it home clearly. So may I interrupt the quote there a minute? If I get feisty and ram things home tonight, I can be forgiven. Because Richard Dawkins does that through 300 pages of this book. And he said William Paley was pretty good at it too. I am passionate about this, and I make no excuse for that. And I will tell you, in our common parlance today, and especially in scientific classrooms, folks get plenty of the other side of this argument, and almost none of the argument from design. So I'm happy to share some things with you this evening. And let me add also to that, by way of introduction to this series, I do not ever want you to accept what I say because I said it. You are more than welcome to come and ask me where my references are, and you can check everything I said for yourself. And I'd prefer you do that. Not believe it because I said it, nor should you believe it because some other science teacher tells you. Be convinced by what is really the truth about the natural world. Back to the quote. He had a proper reverence for the complexity of the living world, and he saw that it demands a very special kind of explanation. The only thing he got wrong, says Dawkins, admittedly quite a big thing, was the explanation itself. He gave the traditional religious answer to the riddle, but he articulated it more clearly and convincingly than anyone had before. The true explanation is utterly different, and it had to wait for one of the most revolutionary thinkers of all time, Charles Darwin. So Richard Dawkins expresses his reverence for Charles Darwin. I prefer, ladies and gentlemen, reverence for God. And Charles Darwin is far from explaining origins. So let me pause now a moment and tell you the story of natural theology. Here's basically Paley's argument. If you were walking across a heath in Britain, in England, and you stumbled across some rock, you kicked the rock, and you ask yourself, well, how'd that rock get there? Well, probably your first question is, I could care less. It's a rock. It might have been there forever. But if you kicked the rock over and there was a watch lying there, and you picked it up and examined all those characteristics of a watch, you would most likely ask yourself, how'd that get there? And probably wouldn't say it just happened to come about by natural causes. Because of all the features of that watch, one would most likely conclude it was designed by some intelligent being. That was Paley's argument. And he said, and by the way, the human body and lots of other living things are much more complex than a watch ever dreamed of being. They speak, they testify to a designer. Here's what Dawkins says about it. Paley's argument is made with passionate sincerity and is informed by the best biological scholarship of his day. But it is wrong, gloriously and utterly wrong. The analogy between a telescope and an eye, or between a watch and a living organism, is false. All appearances to the contrary, the only watchmaker in nature is the blind forces of physics, albeit deployed in a very special way. A true watchmaker has foresight. He designs his cogs and springs and plans their interconnections with a future purpose in his mind's eye. Natural selection, the blind, unconscious, automatic process which Darwin discovered and which we now know is the explanation for the existence and apparently purposeful form of all life, has no mind. It has no mind. It has no mind's eye. It does not plan for the future. It has no vision, no foresight, no sight at all. If it can be said to play the role of a watchmaker in nature, it is the blind watchmaker. And that's where he gets his title. So for Richard Dawkins and what he claims Charles Darwin propounded, natural selection acting upon natural variation is sufficient, ladies and gentlemen, to account for all living things. And it did it blindly by the blind forces of physics. And that's sufficient. And then he spends the next 300 pages trying to convince you that that is the case. Is it reasonable to believe in God in this scientific age? Dawkins would say, you're a fool if you do. Because science has displaced the necessity for God. That is a common story in our age. Part of the reason I do this series, because when I was your age, young people who are in college, was deeply disturbed by all of this and did not have good answers and wondered if I studied deeply enough in the sciences, would it automatically cause me to lose my faith in God? And I want to tell you, young people, 50 years later, my faith in God is stronger than ever, not less. And my answer to this question, I'll say at the beginning and I'll say it again at the end, is there is less excuse than ever in this scientific age of missing that there is a God. And that's what I want to try to help convince you of. And we're going to do it by using the argument from design. All right, class, are you ready for a chemistry lesson? Your favorite subject of all time. If it isn't, it's because you didn't have me as your teacher. So get ready for a chemistry lesson. I start this way. What you see before you is a page from the website for SETI, S-E-T-I, Search for Extraterrestrial Intelligence. And there's a statement from page 1. SETI is an exploratory science that seeks evidence of life in the universe by looking for some signature of its technology. Did you know, folks, there are people every day and every night searching the heavens for evidence of intelligent life out there in the universe? That movement started when I was at Harvard University in the 1960s. I studied under a world-famous radio astronomer at Harvard who was in the middle of this. You see all those gadgets there? Those are radio telescopes. They're all over the world, all different places. And these radio telescope experts cooperate with one another around the world, and they set up these ways of examining different places in the universe to see if they can find evidence of intelligent life out there. For 25 years, that was funded by your tax money, starting in the early 60s. After 25 years of finding exactly nothing, they quit using your tax money. But it is still being funded by private sources to this day. There's the website. You can go look for yourself. So what do? Typically, radio SETI experiments have looked for what are called narrow band signals. These are radio emissions that are at one spot on the radio dial. On the way over here from supper tonight, I was listening to FM 96 point something, and it had some beautiful music on it. You know you can turn on your radio dial to a specific spot and you can receive signals, right? Language, sounds, music. What people know is narrowband radio signals are the mark of a purposely built transmitter. Natural cosmic noisemakers such as pulsars and quasars do not make radio signals that are this narrow, and I might add, that contain information. So what are the SETI folks looking for? They're looking for signals from outer space in some narrowband radio signal that has information in it. Because listen to me, folks, nobody thinks nature could produce such a thing by itself. That is the sign of a purposely built transmitter. That means somebody built it. And they would tell you, if they found such a thing, it would be tremendously powerful evidence that there's somebody out there in outer space that is intelligent. This is extremely important. Did you get it? It's only the foundation for everything else I'm going to say. And I'm all for this. I'm not against this. And I would absolutely believe if they found such signals from outer space, that'd be powerful evidence that somebody out there is intelligent enough to build a transmitter and to do the stuff that it takes to get this to happen. Since the early 1960s, they have found exactly zilch evidence. Does that mean there isn't anybody intelligent out there? I don't know the answer to that, but they haven't found it yet. And that makes no difference to me. What makes a difference to me is if they did, it would be powerful evidence for intelligent design. And I'm asking the question, why can't we do that same thing right here on Earth? I think we can. And by the way, they can infer intelligent cause in this instance without identifying what that intelligence is. That's another important point. Suppose we did get a radio signal that had in it some kind of a message. What would we know about the intelligence out there? Only that we got this signal. That's about it. So you can infer intelligent design without really knowing everything about that intelligence because it has the symbols and the properties of something that was designed. If you were in my class and I pause, that means it's going to be on the test. Get it? What if we received a message from space that had a language in it that we could decode and read? I'm going to quickly tell you, we have not received any such thing. But what if we did? I would argue that's powerful evidence. There's something intelligent out there sending signals. It isn't the stars bleeping something. So I want to turn our attention not to outer space. And by the way, come back Wednesday night because we're going to talk about the macroscopic Wednesday night. Tonight and tomorrow night, we're going to talk about the microscopic. So I want to look down inside living things at the smallest things we know about and look for design at the microscopic level. We're calling it the signature in the cell. and it's taken from the website. You remember they said they were looking for some signature of its technology? There's a book called Signature in the Cell. What happened here, gentlemen? I hope nothing. That is not good. Say it again. No. We're not there yet. So you blanked me out. Is that what happened? I feel good. That was an intelligent source back there. That didn't happen by accident. I want to stay here just a minute. The book Signature in the Cell by Stephen Meyer. I would highly recommend it to you if you want to really dig in. You see how thick it is? Stephen Meyer is a phenomenal writer. He's a philosopher and a scientist. And well-read, he studied at Oxford, folks, the same place Charles Darwin studied. He's brilliant, and he's a believer in design. We'll come back to that in a minute. So is there a signature in the cell? Well, here's what I would say to you. There are signs of intelligent design everywhere you look here on Earth. You don't have to look to outer space. Every living cell is full of signs of intelligent design, including a language which we've learned to decode and read. So Anthony Flew, professor of philosophy, former atheist, author, and debater, debated many creationists like me and belittled us for believing in God. Anthony Flew. When he was 80 years old, he said this: "It now seems to me that the findings of more than 50 years of DNA research have provided materials for a new and enormously powerful argument to design." And Dr. Flew has become a believer. Now, he doesn't believe in the Bible yet. I don't know if he's still alive, but when he turned 80 in 2004, he became at least a believer that somebody had to design what we're observing in the cell. This didn't happen by natural causes. Charles Darwin, to the contrary, notwithstanding. I appreciate an 80-year-old man that'll change his mind on something as significant as that, based on the evidence of the natural world. Research on DNA continues to reveal signs of design. It's beyond belief. I hope I have the capacity to give you some little hint of what's going on here before you fall asleep. And for those who weren't here yesterday, I don't allow sleeping. If I see you sleeping, we're going to stand up. Anthony Flew said, "I have to go where the evidence leads." That's all I'm asking you, class. And if you're here tonight and you're not a believer in God, thank you for being here and opening your mind at least to listen. And I hope you're of the nature that you'll follow the evidence where it leads, even if it goes against what you think. And I hope I'll do the same thing. So there's the book I've referred to, Stephen C. Meyer, Signature in the Cell. Now let's talk a little bit. Which is more reasonable, class? Natural causes or intelligent design? Listen to me closely. There are no other answers to this fundamental question. Where did living things come from? They either came about by natural causes or they required intelligent design. If you know some other answer, would you please tell me sometime? There aren't any other answers. Either nature did it by itself, without any God whatsoever, or there was intelligence required in making living things. I don't think there are any other answers. So which is more reasonable? You're going to look at the evidence of the facts of nature, and I'm going to ask you, which is more reasonable? ladies and gentlemen of the jury. That's the best you can do in science. And by the way, nothing's 100% either. There will always have to be an element of faith. Always. So, may I introduce you to living things? And by the way, I'll probably say throughout this, and there's lots of things in books that say this, life as we know it has these characteristics. Could I suggest to you there is no life but what we know about? I mean, anything else, we don't know about it. So saying life as we know, why don't you just say life? And because people want to leave open the idea there may be some other kind of life. Well, if there is, nobody knows anything about it. So could I say to you, the only life forms we know anything about have certain characteristics. So I'm going to read you from a little book called Life Itself, Its Origin and Nature by Francis Crick. Now this is a class, so you can answer my question. Who can tell me anything about Francis Crick? Anybody? You biology kids? Tell us about Francis Crick. Louder. Thank you. Watson and Crick were the co-discoverers in the anybody know? 53. They received the Nobel Prize for discovering the structure of DNA. One of the most fascinating stories in the history of science. And may I tell you, class, that since 1953 until this present day, we've learned more about how life functions at the biochemical level than all the history of mankind before that. You live in a privileged age. We know more about how life functions now than we ever dreamed of. And may I suggest to you, we haven't touched the hem of the garment. But what is life itself like, according to Dr. Crick? If anybody knows, he ought to. So I'm going to read you from page 72. Life as we know it on Earth appears to be a synthesis of two macromolecular systems. And I just lost you, right? Macromolecular means huge molecules. Two systems of large molecules. Every living thing consists of these. The proteins, because of their versatility and chemical reactivity, do all the work, but are unable to reproduce themselves in any simple way. So you got the proteins. The nucleic acids seem tailor-made for reproduction, but can achieve rather little else compared to the more elaborate and better equipped proteins. So proteins and nucleic acids. Every living thing has them both. That's what life's about. Here's a little breakdown of that. We have structural materials that are made up of proteins, assembled from amino acids, that make up the construction, the shape, and mobility of living things. But they're proteins. Then there's the tools and machinery. They're called enzymes. They're special forms of proteins. And they make up the metabolism, the growth and maintenance of living things. But please note, class, that both of those groups are proteins. Okay? That's one class of molecules. The other great class is called the blueprints. They are the genes, the nucleic acids, the DNA and the RNA that have become common to everybody's language these days. And they provide for reproduction. They contain the information and the directive function for reproduction. Now listen to what Crick says. The problem of the origin of life. How did life get started, class? Dawkins says it came about by a lot of small-scale changes over millions of years directed by natural selection with the blind forces of physics. The problem of the origin of life would be a great deal easier to approach if there were only one family of macromolecules that does both jobs. But life as we know it always employs two families, the proteins and the nucleic acids. And there is zero evidence that you don't have to have both. Now, I was alive in 1953. I was in elementary school. And I've been through this the last 60 years as people have tried to explain how did life get started with either just proteins or with just nucleic acids. And it's been a total miserable failure. We don't have a clue, ladies and gentlemen, 60 years after we discovered nucleic acids. In fact, we know less about how life originated than we did then, than we thought we did then. It is so complex and it's unbelievable. So Crick himself admits it's kind of a difficult problem here. How did life get started in the first place? Because you have to have all of this working together in harmony to make living things. So you know what he does for the rest of this book? It's hard to believe, but I'm going to tell you, he spends a good section of this book talking about directed panspermia. You ever heard of that? It's the theory that the first living things were sent here on a spaceship from outer space. I'm serious. This is the Nobel Prize winner. Is there one scintilla of evidence that a spaceship brought some simple life forms to this earth? No, there's not. But our Nobel Prize winner would rather take that than God. And so he spends about 6 chapters. He's talking about how the spaceship would look, what kind of stuff it might have sent. It's beyond belief. It's a bunch of fairy tales. But that's the majority of this book. From one of our experts on life. Let's talk a little more about proteins. There are 2 types of proteins, structural and enzymes, basically. They're the workhorses of every living thing. And I offer my apologies to every protein for the incomplete, inadequate treatment I'm going to give it for you tonight. We should spend 6 months on this. And if you were in my chemistry class, we would. Here's what they're made of. I'm going to give you a little time to look at that. The quiz is in the morning at 8:15. Glycine, alanine, valine, leucine, isoleucine, proline, and so on. Do you notice they all end in INE, except that one? And that one. Why are they called amino acids? Let me just show you a little bit of chemistry here, okay? You'll notice every one of these chemical formulas for these amino acids has an NH3 group in it. You see that? Every one of them, NH3. That's called an amine group. So every amino acid has an amine in it. So why is it called an acid? Because, you see that little COO group right there? That's a carbon attached to 2 oxygens. Every one of them has one of those. Can you see that? If you want to pronounce it, that's COO. But COO in chemistry is an organic acid. So they're amino acids. And if you were in my chemistry class, we were studying biochemistry, you would memorize the 20 common amino acids by tomorrow. Right? Of course. And you would learn their names and their abbreviations. The next day, you will learn their chemical structures. Why is that, class, do you think? It's only the foundation of everything else we're going to talk about. That's why. Because a string of amino acids makes a protein. Are you listening? A string of amino acids makes a protein. And proteins are one of the building blocks of life. Critically important. Every protein is a combination of these 20. It's very much like in the English language. Every word in English is some combination of the 26 letters of our alphabet. Even anti-disestablishmentarianism. Isn't that a combination of the 26 letters of the English alphabet? It is. Every word in English is some combination of those 26 letters. In proteins, ladies and gentlemen, every protein is some combination of those 20 amino acids. You got it? I'm sorry, I have to use this book one more time. Here is a quote from Dr. Crick. RNA and DNA are the dumb blondes of the biochemical world, fit mainly for reproduction with a little help from the proteins, and he ought to be ashamed of himself. It should say, with a lot of help from proteins, but of little use for much really demanding work. I'm sorry, blondes, I didn't say that. It's probably the one thing you're going to remember. RNA and DNA are good for reproduction. That's about it. Do living things have to reproduce? They absolutely do. But you have to have RNA and DNA and proteins in order for that to happen. Not one without the other. And why is that? Because really the RNA and the DNA are kind of like dumb blondes. Good for reproduction and not much else. Now, I don't believe that. Everybody, blonde, smart people. But it makes a good point. And I didn't say it, he did. So now, having done this wonderful treatise on proteins, which was so pitiful, I'm now going to turn my attention to the DNA, the other two huge class of molecules. Very important. You need to learn about DNA because it has a certain characteristic structure. You see these two strands wrapped around each other? There's one back there and there's one out here. It's like this. And then you just see there's cross pieces that connect them together. That is the structure, ladies and gentlemen, that Crick and Watson discovered in the 1950s and for which they were given the Nobel Prize. It's one of the most amazing discoveries ever because it is that characteristic structure, a double helix with crossbars, that allows the living things to reproduce themselves. And without that, it wouldn't happen. But I want to say again, the DNA by itself will never reproduce anything. You got to have, and I guess I'm going to start here now. I'm going to ask you some questions going forward. To almost every question I ask you, the answer is protein. Okay? So I'm going to say it like this. DNA gives the capacity to reproduce, but it can never do it without. Thank you. Now you stay alert. The DNA double helix is unwound by RNA polymerase, giving the enzyme access to the nucleotide sequence. You see the DNA right here? It unzips. You see that blob right there? It's called RNA polymerase. It is a, good job. If you see a word in chemistry that ends in ASE, it's an enzyme. And an enzyme is a special case of a, exactly right. So class, what does it take to make DNA unzip? A protein. exactly right. In fact, that glob right there is more than one protein, as you'll see in a minute. But when the DNA unzips, it exposes two sides here. You see that? On this side, there are these letters, A, C, G, T, A, G, G, T, A, G, C, G. There are not letters sitting on the side of DNA. Those stand for four chemicals called adenine, thymine, guanine, and cytosine, which stretch along the strand of the DNA. The letters are there to help you identify what the chemical is. So you don't unzip the DNA and say, oh, look at all those letters. No, look at all those chemicals. But I will tell you what we've learned. If you want to start over here and start reading, we've learned how to read. Because tied up in this strand of DNA is a language. And every word in that language has three letters. Kids, wouldn't you love to have a language with just three-letter words? Spelling would be so easy. But the fact is, it's a language. So C-A-T, which means a little furry creature that runs around in your house, not in genetic language. It means something very specific. C-A-G means something else. A-C-G, G-A-T, T-G-A, and so on. Every three-letter word in that sequence means something, class, and we've learned exactly what it means. And here's what it is. What you see before you is a mapping of the genetic code. On this side, we have the letters for the first letter in the three-letter word. Across the top is the second letter, and down this side is the third letter. So you can form every possible three-letter word using four things. Let's do a little arithmetic here. If you have four things, and you're going to use them three at a time, and you can repeat letters, how many words can you make? A bunch. It's really not that many, to tell you the truth. If you think of a three-letter word, how many different letters could you put in the first position? 4, right? How many in the second position? 4. And in the third position? 4. So it's 4 times 4 times 4. Do the arithmetic. That was quick. You hear what she said? You're right. 4 times 4 times 4 is 64. There are exactly 64 words up there. So I'm going to help you learn to read, class. You ready? We're going to learn to read. You. That's a three-letter word. You pronounce it ooh. This is not a spoken language, okay? That one you could speak, though. What does you mean? It means phenylalanine right there. Let's try another one. What if you did C-C-G? C-C-G. That means serine. Oops, proline right there. Let's try another one. How about UCC? UCC. That's serine. Are you getting the idea? You can read all 64 words off that chart. Now, if you look at it carefully, hopefully you're drawing some conclusions. You recognize those words up here? It's the ones I asked you to memorize a while ago. You already have it memorized, right? Because the test is tomorrow. No, what you find up here, class, is all 20 amino acids. And there's some repeats, aren't there? Do you see repeats up there? Like alanine is listed 4 times here. Aspartate a couple of times. Lysine, leucine several times. There's some repeats. Because there's only 20 amino acids and there's 64 words. I call that a backup system. You have more than one code for some of those amino acids. In addition to that, there's a code right here, AUG, that says start reading. And then there's other codes up there. Do you see them up there that says stop? Those are called terminators. So for example, UAG says stop reading. Everybody's eyes on me. You remember that strand of DNA I just showed you? How do you know where to start reading? There's a code that says start reading right here. And then you start reading 3-letter words. Each 3-letter word is an amino acid, right? And then you stop reading. In between where you start reading and where you stop reading is a strand of amino acids, which makes that is very poor. In between stop and start, there's a string of amino acids which makes that's better. What you have here, ladies and gentlemen, is a language that codes for building proteins. And people teach this stuff as this. Isn't it interesting what nature did? Right. Nature produced a language by itself that you can use to build proteins. And you can believe that? If they received a signal from outer space with this code in it, everybody would say that came from an intelligent source. But if it's in every living cell on this earth, doing its job constantly, at a phenomenal rate of speed, isn't it interesting how small changes over long periods of time and the blind forces of physics produced all this? I can't go there, folks. If we received a message from outer space containing the genetic code, every headline in the newspaper would say, somebody intelligent out there is trying to tell us. But not if it's in every cell and every living thing. The SETI organization and any other reasonable people would certainly conclude this came from an intelligent source. If all you had was the genetic code. But folks, the genetic code is nothing compared to what we know about the cell. It's hardly the beginning of the start of the hem of the garment. There's much more to living things in life as we know it than the genetic code. That's just one small piece. I mean, it's a significant piece. And by the way, if this were a court case, I'd say, I rest my case, class. Ladies and gentlemen of the jury, nature by itself does not produce languages that do things. That requires intelligence. Case closed. But we're not done. Because I want to talk to you about how it works, just briefly. And I'm going to give you a little overview, and then we're going to watch a video clip that shows you a little more detail. You see up here's the DNA in the nucleus of the cell. It has to get copied. That's called transcription. Guess what it takes, class, to help the nuclear DNA get copied? Thank you. One of them's RNA polymerase I just told you about. That's what makes it unzip. But there's a bunch more. Then, once it's copied and transcribed, it has to be processed. You see these little white things here? Those are called introns. They are snipped out, and the thing is matured, and then you have your mature messenger RNA. Guess what it takes to snip out the introns? Good job. The mature RNA then migrates outside the nucleus and is picked up by 2 ducks hugging themselves. Wrong. That's just what it looks like. That's called the ribosome. And it picks up the DNA information. By the way, the copies that are made up here are called RNA. They're the copies. and they migrate outside the nucleus, picked up by the ribosome, and then the ribosome read the information off of the RNA like a tape through a tape player, and out the bottom comes the proteins. Class, guess what it takes to make this read like this? Good. Guess what it takes to build a protein? It takes proteins to build proteins. Did you hear what I just said? It takes proteins to build proteins. Now we got a video clip. Are you ready? Let's go with it. If you want to see this clip again, go to signatureinthecell.com. On the home page, you can find this video clip with their own, what do you call it? Language underneath it. No. It's spoken. The monologue. I'm going to do the monologue, and I'm better than he is. So he's going to play this for me without any sound, right? I'm the sound. So here we go. All right, stop right there. Pause. Now you got to be really fast. When I say pause, that means, all right. What you see before you, ladies and gentlemen, is a cartoon picture of the DNA molecule, right? Double helix with cross pieces. And you see the cross pieces here? By the way, I didn't tell you that every time there's a T, there's an A to match it, and every time there's a G, there's a C to match it. Like love and marriage and a horse and carriage. Okay, let's go. Move forward. So you're watching the DNA here, and it's just a beautiful strand containing all this information. Keep going. Stop. Now, you see this blob right here? That's RNA polymerase and its companions. You see all the different colors? That's really several different proteins that are riding along the DNA strand. If you didn't have that, ladies and gentlemen, there would be no reproduction. You have to have RNA polymerase to unzip the DNA to get the information off of it, which then is used to build a protein. Okay? You have to have proteins for this to work. So can I interrupt here just a minute? Where'd the first RNA polymerase come from? You had to have RNA polymerase to make RNA polymerase. Sounds like somebody had to start this to me. Like design it? It makes no sense otherwise. All right, here we go. We're watching the RNA polymerase as it rides along the DNA. And then we're going to go, look, stop right there. That's really more what it looks like, kind of a glob of protein stuff surrounding the DNA. Now we're going to go down inside that glob, and we're going to look at what's happening inside. So go ahead. Right there, stop. Do you see now that the DNA is unzipped? And exposed are two sides. I can tell you that in the 1950s and early 1960s, when we were first learning all this stuff, we thought that only one side of the DNA was copied. Now we know better. Both sides are copied. And they're used for different things, as you will see later. But there's information along this side in the form of three-letter words formed with adenine, guanine, cytosine, and thymine in sequences. And what the cell does is it brings in, and each piece is copied with the exact mirror image of that piece right there. So if that's a T, you're going to have an A over here. If that's a G, you're going to have a C over here. So it's exactly matching up. And listen, if you were in my chemistry class, you would tell me why is it that T always goes with A? It's because of their chemistry. Their molecular structure is what allows them to connect up. So let's watch a little bit. Go ahead. Can you see that each piece is coming up and forming the information copy? Stop right there. One of the problems with this little video clip is it's way too slow. Look at me. That happens about like this. And that was way too slow. That happens in milliseconds. Go ahead. They're going to try to speed it up a little bit so you can really see. Okay, stop. Now, do you see the RNA coming out this side here? That's the copy of what's on the DNA coming out the side and being released into the cytoplasm of the nucleus, containing the information that it got off the DNA. If that's all you did, class, you'd have nothing except a copied piece of information. Guess what it takes to make all of that happen? All those copies. Say it. Proteins, yeah. Okay, now we've got it migrating, you see? Let's keep going now. It's going to start migrating through the nuclear cytoplasm. And watch carefully as it now comes to the nuclear wall right there. Stop. Did you stop? I didn't think so. All right. Do you see that hole right there, class? Guess what it's made of? Good job. Do you think that any respectable nuclear wall is going to let just anything pass through? The answer is no. Only certain things get through the nuclear wall. So watch. That wonderful protein sitting there is a guardian of the gate. So when this RNA comes up, go ahead. This guardian of the gate says, "Welcome, Mr. RNA. You may come right through into the cytoplasm." See it coming out here? Stop right there. On this side of the hole, there's another that guards going back in. So there's another protein, ladies and gentlemen, in the process, right? That guards the gate. Now we continue. The RNA now comes over here to the ribosome, which closes in on it and begins reading the information off of the RNA. Stop right there. We're down inside the ribosome now, okay? And here is the RNA with the code on it. CAC, ACG, CUA, CCG. Each one of those stands for an amino acid, remember? Now here's what happens. This is called a transfer RNA. He looks like a little seahorse, doesn't he? Not really. But that little seahorse, transfer RNA, is carrying the specific amino acid that corresponds to that three-letter word. I'm going to say that again because I lost 2/3 of you. This is transfer RNA. Have I said one thing about that yet? No. But it's all part of this process. It carries the specific amino acid that corresponds with that three-letter word. Do you notice there's quite a distance here between those two things? The code is up here and the amino acid is here. That's because this RNA is so designed that it gets the matching amino acid for that code. I don't know how you're feeling. This is unbelievable, isn't it? And guess what it takes to make the transfer RNA pick up the appropriate amino acid and bring it in there to copy? Guess what that takes? There is a specific protein for every amino acid. So there's 20 of them. You just named 20 more proteins that are needed to make this happen. Am I explaining to you how all this happens? No, I'm just touching the hem of the garment. Keep going. See, what happens is, stop. You now have 1, 2, 3, 4 amino acids in a row. They're all combined here by chemical bonds. And you now have a protein that's 4 amino acids long because you've made 4 of these copied and built it. So what happens is you keep reading 3-letter words, the specific transfer RNA comes up there with its specific amino acid, it's hooked onto this one, and then you go to the next one. And you build a protein. Okay, let's let it go for a little bit. And you know one problem with this? It's so slow, it's pathetic. Speed it up. Let's move it. Come on. They try to make it look right. That's way too slow. Pitiful. Stop. All of that was done many seconds ago. And out the bottom of this ribosome, can you see it right there? That's the protein coming out. This is the RNA being read and then released. And by the way, it gets to be reused. And all that transfer RNA that brings in the amino acid, it gets to be reused. It's like recycle. Go ahead. Here comes the protein out the bottom. And when it's finished reading and getting all, stop, whoops, we lost it. There it is. It looks kind of like a glob, doesn't it? We're not finished, ladies and gentlemen, because that protein is useless until it is shaped into the specific 3-dimensional configuration that makes it do its job. It's not just a string of amino acids like this. It wraps around itself, and it has to go into this particular organelle. Let's go ahead. Where it goes inside, and inside it is shaped into its particular 3-dimensional configuration. Stop. And then it turns white. No, it doesn't turn white. All that means up here is it's finished. But did you notice what it was doing? And when it's finished, it's got the exact 3-dimensional configuration with all the right amino acids in order to go forth and do the job for which it was designed. And isn't it interesting that biology textbooks describe it exactly that way and then say it was not designed? This wasn't designed. This was done by the blind forces of physics. Nobody designed this. It is Isaiah seeing they cannot see and hearing they cannot hear. You almost have to want to miss this. Go ahead, let's finish it. Then it is released into the protoplasm to go forth and do the job which it was designed to do. My preference, class, is to admit that it was designed. And it makes abundant sense to me. And it's not eliminating science to say that. There are people who are afraid today, if you become a creationist and you say there is a designer, you're just going to give up science. Did you know it was creationists who designed science in the first place? We're not going to give up science because we believe in God. We're going to examine God's marvelous nature even more thoroughly. Try to understand it better. Okay, can you get me back to my slides? Let me ask you, class. That stuff back there they're working on, did somebody design that? Those computers, they can click it around and toggle from here to there and put that stuff back up there. Does anybody in this room believe the blind forces of physics could have made those computers? Nobody believes that. Nobody even believes that you can send a narrowband radio signal from outer space with information in it without intelligence. And somehow we think this amazing process came about by Charles Darwin's natural selection. You can believe that. I got a bridge I want to sell you. My apologies to this process, because we have not touched the hem of the garment of what all's going on. It's way more complicated than all of this I've said. And it all works together like a finely tuned machine. A living cell is a marvel of detailed and complex architecture, says Carl Sagan, one of the great atheists of our time. But did you notice what word he used? Architecture implies to me an architect. Seen through a microscope, there's an appearance of almost frenetic activity. On a deeper level, it is known that molecules are being synthesized, that's made, at an enormous rate. Almost any enzyme, class, what's an enzyme? A protein, catalyzes the synthesis of more than 100 other molecules per second. You know how you catalyze a molecule? You speed it up. And that process I just showed you, that happens 100 times per second. No wonder you get tired just sitting there listening to me. Your body has been building billions of proteins and other molecules every second that you've been sitting there. You better be eating your amino acids. You get tired from just sitting. No wonder. In 10 minutes, a sizable fraction of the total mass of a metabolizing bacterial cell has been synthesized. The information content of a simple cell, God forbid that he ever said such a thing, simple cell, has been estimated as around 10 to the 12th bits, comparable to about 100 million pages of Encyclopedia Britannica. Carl Sagan said that in 1974. He's dead now. I wonder what he'd say in 2019. We have learned so much since 1974, and it's 10,000 times more complicated. Folks, the living cell is more complicated than all the cities men have built in all this earth. But it happened by natural selection, by the blind forces of physics. Over 200,000 molecules are being built every second in every cell in your body. If we received a message from space containing just the genetic code and an explanation of how it's used to build proteins, everyone would conclude the source was intelligent. There is no question about that. But you try to teach this in a biology class in any of our schools, you'll be crucified as a religionist. Have I said one thing about religion tonight? I have not used the Bible. I would not use the Bible in a biology class. Let's just look at the evidence of the natural world and tell me this wasn't designed. That's all you need to do. Let the kids decide for themselves. And then there was a Human Genome Project. You all know, don't you, that the human genome, its DNA, has been completely mapped in your lifetime. That's an amazing feat. And we've learned so many fascinating things about the human genome, one of which is this. Lots of folks who studied DNA say to us now, 95% of the DNA is not used to do what I just showed you. You know this process of building proteins that I just described? We have learned that only about 5% of the DNA is needed for that. And the conclusion of many scientists is the rest of that in DNA is just a bunch of junk. And do you really believe God created something that was 95% junk? And by the way, in that junk, there's a whole lot of stuff that sure looks like junk. So the evolutionists would say, don't tell me God designed that. That's a better example of evolutionary process where there's so much junk left over from all the changes that were made by the blind forces of physics. So they use it as a powerful evidence against God. That's my subject tomorrow night. Don't you miss it. I say, everywhere we look, from macroscopic to the microscopic, things look like they're made. There's a loud, clear, piercing cry of design, says Dr. Michael Behe, a biochemist, in his wonderful book, Darwin's Black Box. And I say, amen. Is it reasonable to believe in God in this scientific age? I say to you, class, it is more reasonable than ever. The more we learn, the more reasonable it becomes. That this was designed. And that's the lesson for tonight, incomplete as it was. Okay, we're in a church building. The tradition in this church is we don't have services like this without concluding the service by turning our attention back to the Bible. I have zero hesitation talking about the Bible. I believe it's God's Word, and that's another whole subject we ought to talk about. You cannot learn what God wants you to do as a human being made in His image from looking at DNA. Sorry. It's not enough. You need revelation for that. And God has revealed Himself in this book. And He sent His Son, the Bible teaches, to save us from our sin. Jesus said, "Let not your heart be troubled. You believe in God, believe also in me." So I'm here to tell you tonight, if you become a believer in God, the next thing you need to investigate is what has God done for us? And that's what that book will tell you. And the message is, He sent His only begotten Son, that whoever believes in Him should not perish, but have everlasting. And that's the plea. And He's gone back to heaven. He's waiting to come back. But He is coming back. And He wants to take all those who are His into His arms and take them to heaven. But you got to be His. So are you a believer in Jesus Christ? Here's what He told His disciples. You go and preach to the whole world and teach them the gospel message about me. He who believes and is baptized will be saved. So we don't ever want to leave a service like this without saying to anybody here who's a believer in Jesus, why are you waiting? You need to be baptized in water for the remission of your sins. That's what Jesus said. And then you rise to walk a new life. So if you're ready, we've got a song leader ready with a song selected. And if you want to come, we're going to stand, and you come while we stand and sing.
Have you a heart